Merci pour cette introduction. I will continue in English as my topic is something that is touching your interest. Cellulose is the major polymer on Earth, and the major quantity of cellulose is contained in wood and other lignocellulosic materials, some of which were mentioned today already. And the annual rate of production of cellulose per year is really amazing. As you can see here, 1.5 teratons. It has a fascinating molecular and supramolecular structure which explain its abundance on Earth. It is constituted from glucopyranose, which is present in its conformation C1, putting its carbon 1 below the plane of the chair 1, meaning 1 goes down. And we see the distribution of all of the hydroxyl groups in very favorable equatorial positions, which explain why glucose is one of the most abundant molecules on Earth and why cellulose, which is constituted of glucose, is so important on Earth. It also belongs to the family of hexogens. It shares the same structure, molecular structure, in terms of number of carbons, hydroxyl groups, and oxygen. The same family as starch and inulin, which is constituted from fructose. And here is the general formula for all hexogens, where we put forward, highlight the 3 hydroxyl group, which are important for us in discussing the derivatives of cellulose, which are actually acting with those 3 hydroxyl groups. What is very fascinating about cellulose is, despite this abundance of hydroxyl group, cellulose is a solid material, very solid. We have tried many means of transforming wood into different biopolymers. Cellulose always remains solid, despite how harsh the conditions that we apply. This is due to the formation of the intramolecular and intermolecular hydrogen bonds. Intramolecular hydrogen bonds goes from one and the other side of the cellulosic chains, and they keep cellulose in this rigid, extended shape. And the intermolecular hydrogen bonds explain the tendency of cellulose to form different types of associations or bundles, which we will name with different names depending on the means of the devices by which we are studying. So the common name is microfibril in what concerns wood science and wood engineering. And here I highlight the 2 types of intramolecular and 1 type of intermolecular hydrogen bond. What is important here to note is that the cellulose is actually in its native state, which we indicate as cellulose 1. It is organized in sheets, and the hydrogen bonding between the parallel chains is only in the sheets. And the sheets are united only by lower energy intermolecular interactions type of van der Waals, which keeps them all together. And this is very favorable to you guys who want to produce the nanoparticles from cellulose, because that's how you make it possible to separate different sheets and to get access to the nano size particles. And this is a very important property of cellulose 1. And then we mentioned, your question was something about exactly cellulose microfibers. This is one of the first lectures that we give to the students. That's how they study the structure of wood cell walls, especially of tracheids in softwoods and fibers in hardwoods. The structure of the other types of cells is even more complex, but this is the usual type of scheme that we present, where we speak about the more or less organized domains in the microfibers of cellulose, some of which are really characterized by true crystallographic means, as there are really micelles of crystals. And these explain these extremely rigid structures of plants, and which enable the plants to grow in a very big height. But we shouldn't forget about lignins, which are not the topic today, which contributed actually to the growth in height. And finally, here is the representation of the cellular ultrastructure. Cellulose wood cells are always multi-layered, and the cellulose microfibers are very favorably oriented in the most important layer, which determines the properties, mechanical properties of wood and its uses. So here I wanted to mention the multiple sources of cellulose for what concerns us. It is mainly the cellulosic pulp, which is used in paper making, and it is the starting material for the most important starting material for different nanoparticles. And once we get access to cellulosic pulp, we need to bleach it to get rid of the remaining lignin. And then we get access to something that is called dissolving pulp, which is very highly pure cellulose, which is then acceptable for production of different types of cellulose derivatives, esters and ethers that are interesting for you as potential hydrocolloids. And also it is the type of material that is used for production of regenerated cellulose, which is cellulose 2. And finally, for the nanoparticles, which is the topic of today's presentations, as you are interested in 3D printing. But when I was invited for this lecture, I really realized that cellulose has played a role in a historic event, which is the invention of printing, which really marked the history of humankind, because without Gutenberg and printing, and even before Gutenberg, the Chinese have invented the same type of printing, but they are not so recognized. 2D printing has been made possible with the Gutenberg's pressing machine, which was designed completely in wood, 100%. It was later upgraded to include the metallic parts, and the printing has been done on paper, which is very much rich in cellulose. So even if it is of textile, if it was of textile origin, it is still the same molecule. And we are witnessing today the return to cellulose as a fantastic, amazing material which will make it possible to create new objects and new applications. And I just wanted to show you something that is, for me, particularly amazing. This is a woodcut print, gravure sur bois, of the famous graphic artist Albrecht Dürer. And it illustrates perfectly well two very important properties, both of scientists and of artists. And this is the imagination and creativity. He has made the design for this woodcut without having ever seen a rhinoceros. He has never seen it. He has only designed it from the description from someone who has seen it in Lisbon. And I always found it very amazing. And anyway, the printing with the woodcuts was historically very important as it exploited the properties of wood and of cellulose itself. And now we are witnessing the new applications of cellulose in 3D bioprinting or additive manufacturing, where the plant-based materials benefit of harnessing plant structure in architecture combined with their inherent bioactivity. And I have noticed the mention of geometry very much in what was exposed today. And geometry was the fascinating thing in the 15th century when the printing machine was invented, that when the first books, so-called incontournable, were designed, as those people who included Albert Dürer, but also Piero della Francesca, have been the masters of geometry and perspective and mathematics. That's a very important thing not to be forgotten. So the cellulose is coming back in a different way for different purposes. And the 3D printing is, I think that I don't have to go through the different ways. We are going to see all this in the afternoon, different types of 3D printing, which is mainly based on the cellulose is mainly added as rheology modifier in all kinds of extrusion printing or jetting printing. And it is also amazing for me that the printing, that the inks themselves, the first inks were designed from wood products also. It is historically also very interesting, and we are coming back to a wood constituent which will constitute the future inks for 3D printing. The first inks with which designed Leonardo da Vinci, for instance, his designs are with so-called iron gall inks, and iron gall are tannic extracts from some types of galls which grow on oak wood. So with polysaccharides, I've noticed that a lot of 3D printing call for matrices made of hydrogels, and one of the hydrogels that is very often called for are alginates, which are constituted from D-manuronic acid and its 5-epimer. Epimer in chemistry, those who are familiar with the chemistry of carbohydrates, are the stereoisomers, which only differ on one single carbon, the configuration of which. And so that's how the glucuronic acid, which is the 5-epimer of monouronic acid, brings us into the series of L sugars. And this is the short scheme of the alginate structure with the parts of monouronic and glucuronic acid and combination of two. And again, it is the combination that will define the properties of the matrices. This is very important. And then we have the different types of nanoparticles of cellulose which are available. We have seen some discussion about nanocrystals of cellulose. Here I just cite some of the dimensions, but there are different types of dimensions. Anyway, the tempo oxidation of the cellulosic materials provide introduction of, again, uronic acid groups, which provide the possibility to put away the cellulose, to prevent the cellulosic chains to get together. And that's how the nanofibrillated cellulose is produced by combination of tempo oxidation and ultrasonication. And then nanocrystalline cellulose is usually produced by harsh conditions and application of hydrolysis. Well, that's how we get rid of the amorphous portions and get only the crystal ones. So the nanocrystalline cellulose is applied mainly to modify the rheological properties and is used in scaffolds and in tissue engineering. And the same is applicable to nanofibrillated cellulose, which is also often used in combination with the alginate matrices and in tissue engineering. Then we have a group of cellulose derivatives. I fail to say, but the nanocellulose and nanofibrillated cellulose are mainly obtained by intervention on the supramolecular structure, while the cellulose derivatives are really changing the molecular structure of cellulose by substitution of its hydroxyl groups, its alcohol hydroxyl groups by different agents. And here I presented methyl cellulose and carboxymethyl cellulose, which is also introducing the negatively charged group. And finally, the hydroxypropyl methyl cellulose, which is also used as a hydrocolloid. And these cellulose derivatives have found application in 3D bioprinting, and I found some references to that end, which I cite here. And in the conclusion, what we can say is that we can, by modifying cellulose supramolecular structure, we get access to the nanoparticles of cellulose, both nanocrystalline cellulose and nanofibrillated cellulose, while by the changes at the molecular level, we get access to ethers and esters. I didn't speak much about esters, but they can be used in their own right for all cellulose materials, while using, for instance, acetates, which are solids. We can see that modifying a number of sources are really illimited. We are currently working with rice husks cellulose. We tried also wheat cellulose and with many celluloses from wood. And the number of sources is really enormous. And then the methods of their isolation and modification are also very numerous. So there is a huge potential of innovation in this field. Because as you know, as engineers, most of you, you know that the design in engineering is very important, and that different designs will bring different products with very different characteristics. So I believe that the future is for you. Thank you.